Okay, lesson 9.3 continues with the same concepts of 9.2. We're going to look at problems involving motion. So we're still going to be working with our displacement, acceleration, and position functions. Okay, example 1 says an object moves in a straight line with a velocity of 6t minus 3t squared, where velocity is measured in meters per second. How far does the object move in the first second? So how far implies that I'm going to need to know my position function for this question. So let's start with that. Let's find the position function. So I need to take the antiderivative of my velocity function. So S would be equal to 6t squared on 2 minus 3t cubed on 3 plus some constant c. So as I try to find my c value, let's just tidy this up, 3t squared minus t cubed. I have to think about what would be the initial conditions because they don't state. So I'm going to have to make some assumptions about that. So what I know is that at t equals to 0, at time 0, I can assume that this object hasn't actually started to move yet. So then I would know that v would be equal to 0 and s would be equal to 0 too because he hasn't gone anywhere. Okay? All right, so then I can plug in that 0 for t and 0 for s, and I would hopefully see that c would have to be 0 from that. Okay, so from this I would then know that my constant would have to be 0, and so then I get that s is equal to 3t squared minus t cubed. There's my position function. Now, the second part to this is it says how far does it move in the first second? In the first second. All right, so the next thing I actually have to do is check for change in direction. So this goes all the way back to chapter 3, lesson 3132. We need to know if it's still traveling in the same direction. Otherwise, we have to do it in parts to find the total distance it has gone. Okay, so the second thing is I'm going to check change in direction. In order to check change in direction, I need to know what is happening at the velocity. When the velocity is equal to 0, that's when the object pauses and changes direction. So 0 is equal to 6t minus 3t squared, and then I factor that. So I could pull out a 3t, and then I'd be left with 2 minus pardon me, t. And so then I get at t is equal to 0 and t is equal to 2. That's when the object changes direction. So not at t equals to 1, because this question asks in the first second. So then I get to just plug in 1 into my position function. So s of 1 is equal to what? 3 times 1 squared minus 1 cubed. So 3 minus 1 is equal to 2. And we'll put units on that. So it went 2 meters. The object went 2 meters in the first second. Object moves 2 meters in the first second. All right. How far does it move in the first 2 seconds? Well, lucky for us, it doesn't change direction until 2 seconds. So we just get to then also just plug in s of 2 and calculate this one. So now we have 3 times 2 squared minus 2 cubed. So 12 minus 8 is equal to 4 meters. And just make sure you have units. I don't necessarily need a statement on that, but I for sure need units. Okay. The object is backward started at time 3 seconds. How far did it travel to get there? Okay, so is there a way we can do this with some logic as opposed to having to work through our calculus pieces? So let's think about this. What do we know from what we've done already? We know that if an object starts, I don't know, randomly here, and it's traveling forward until time 2 seconds, right? That's when it changes directions. We knew from part B that it went 4 meters. Well, this says that the object is back where it started at 3 seconds. So when it changes its direction at the time 2 seconds, it goes all the way back to where it started. So I assume it's going exactly 4 meters. If it went 4 meters in the positive direction, then on its way back, it would also go 4 meters. So how far did it travel? We would just add those two together. And so the total distance would be 4 plus 4, which is 8 meters. That was okay. Okay. And then question 2. A particle is accelerated in a line so that its velocity in meters per second equals the square root of the time elapsed measured in seconds. How far does the particle travel in the first hour? Okay, so I'm going to note that there's a unit issue here. I'm making my function. Okay, so what do I know about this function? It tells me that its velocity, v, is equal to the square root of the time. Square root of the time, but that one is measured in seconds. And then I'm asked to calculate how far the particle travels in the first hour. So I'm going to have to do a units conversion there. I'm going to need to know that in 1 hour, I'm going to go 60 minutes times 60 seconds, so 3,600 seconds in an hour. Okay? All right, so what else will I note about this function? That at t equals to 0, the particle, we can assume, hasn't gone anywhere, so that the velocity would be equal to 0. And then after that, when t is greater than 0, because it's the square root function, the velocity is going to always be greater than 0. So my particle will always be moving in a positive direction. Always moving in positive direction, which means I don't have to go through that whole factoring scenario like the other question to see if I have a change in direction before I calculate. Okay, so now that I have set everything up, I'm going to need to know my position function. So the second thing would be to take the antiderivative of my velocity. Perhaps you would prefer to write v as t to the power of a half before you go ahead and take your antiderivative. So I would know that s is equal to t to the half plus 1, just to write that out, which is 3 halves. So I'm going to divide by 3 halves plus a constant. So this tidies up to be that s is equal to 2/3 t to the power of 3 halves. And then let's think about what the c value would be. Okay, so if at time 0, if my particle hasn't moved, then s is equal to 0. So hopefully you'll then again notice that therefore then c would have to be 0, right? So if this was put in as 0 and this was put in as 0, c has to come out to be 0. So that leaves my position function s as 2/3 t to the 3 halves. And we're going to now calculate that. How far has it gone in the first hour? Which is going to have to be done in terms of seconds because the function is defined in terms of seconds. So I'm calculating s of 3,600. So 2/3 times 3,600 to the power of 3 halves. We throw that into our calculator and we get 144,000, and the units on that is meters, given the information was velocity meters per second in our initial statement of the question. And then, of course, we could divide that by 1,000 if we wished, and that would give us 144 kilometers. Okay, so there's an or. So just read the question carefully if it asks for it to be in some sort of specific units. Always pay attention to those units. Okay, so I'm going to let you read number 3 and see if you can set it up, and then see what it is that you know. I've given you a nice little picture here in the file. I know it's not in your lesson notes, but maybe that'll help you get yourself set up, and we'll come back in the second video and walk through it together.